Okay, good evening. This is Professor David J. De Los Reyes. Okay, the date for today is October 25, 2023, and the time is around 11:11. Okay, my topic for tonight will be a long video format discussion, and this will be a continuation of my AC machines. And this will now be lesson number 47. Okay, let's proceed. The title of the long video format discussion for tonight will be AC machines, and this is now lesson number 47. We are still on transformer and we are almost done. Okay, because after this I might be discussing the concepts of alternators and the so-called power generation. Okay, so for tonight, I will be discussing one of the last two topics under transformers, and the title of the topic will be SCAT, or capital letter T dash capital letter T transformer, or the so-called TT transformer. We are done with the so-called single phase transformers, and we are done with the so-called study of three-phase transformers, including their voltage and current relations, including the powers like the apparent power and true power. Okay, so for tonight I will be discussing another type of connection of transformers, and this was actually invented here in the USA, and the inventor of this SCAT or the transformer is actually Mr. Or Engineer Charles Pelton Scott. He is actually an electrical engineer from Yale University, and he is from Athens, Ohio, and the year is around 1890. Okay, so the inventor of this Scott transformer is actually Mr. Charles Pelton Scott, an electrical engineer, okay, from Yale University. Yale University is actually from Athens, Connecticut. Oh, that's very near New York. Okay, let's proceed. The why we are discussing another variations of connection of a transformer. We are just bringing it out because this will be another application of the so-called conversion from the main function of a double T transformer is actually the conversion from three-phase to three-phase, meaning the input, the primary connection is three-phase and the secondary connection is three-phase. Or the other variation will be from three-phase to two-phase for wires. And the another application of this will be the conversion from a two-phase to three-phase. So SCAT or TT transformer connection is actually very, what they call this, got so many applications. Okay, from the conversion from three-phase to three-phase, three-phase to two-phase, or two-phase to three-phase. Because with regards to delta or Y, we cannot do anything about it. If it's a single, what they call this, three-phase transformer, we cannot do anything about it for the so-called variation. But if we are given three single phase, okay, we could vary the connections. It depends on how we connect it. Y or delta to Y, or closed delta or open delta. Okay, but for a SCAT connection, a TT, there are three variations on how it will help us. That is from three-phase to three-phase, three-phase to two-phase, or two-phase to three-phase. Okay, let's try to bring out the figure for a SCAT or TT transformer. Okay, the configuration is just like a letter T. That's why letter T. That's why we call it TT. Right? Letter T meaning there is a winding over here, and there's another winding over here, and there's another winding, and so with the other one. Okay? There are three windings in each. That's why the configuration is actually like a letter T. It's letter T. Right? Okay, let's try to define first what is what they call this TT transformer. The concept of this is actually something like this. The transformers are actually connected electrically. They are connected electrically, but not magnetically. They are connected electrically, but they are not connected magnetically. Magnetically meaning in the so-called formulation or the production of the induced voltage, they are not connected magnetically. It is something like this. The first transformer is this one. The second transformer is this one. So actually these two transformers are actually two transformers. Oh, hold on. It will be something like this. This should be the teaser transformer, okay? And this is the main transformer. This teaser transformer has a primary winding and secondary winding inside it, okay? And the main transformer, it has a primary winding and a secondary winding, and we call it a main transformer. So these are actually two separate transformers. Okay, we got 6 terminals coming out from the teaser transformer, 6 terminals. And for the teaser transformer or main transformer, there are also 6 terminals. One of the terminals is the center tap, 2 center taps. And for the teaser transformer, there is a tapping there in which it is called 86.6% tapping. So if you hear the tapping 86.6%, it refers to the teaser transformer. And if you hear the tapping 50%, it refers to the main transformer. 50% meaning if this is a whole winding, okay, if we try to get the middle point of this one, this is 50% tapping, this is 50%, this is 50%, and this is 50%. This is the primary side of the main transformer, and this is the secondary side. So actually, it's a complete transformer containing the primary and secondary, in which the tappings are actually 50%. Okay? For the teaser transformer, there is a tapping, but the tapping is actually a different percentage. It is 86.6%, meaning with respect to this end here, up to here. End to end is 100%. But for it to be a teaser transformer, the tapping is only up to 86.6%, meaning some part of it is not used. Okay, so meaning to say we are bringing out a terminal at the 86.6% tapping for it to fall under a TT transformer. Okay, so according to the definition, the transformers are connected electrically but not magnetically. Because to bring out the configuration or function 3-phase to 3-phase, we must have to interconnect the different terminals. Okay? So actually, this connection is very flexible. If you want a 3-phase to 3-phase, you can interconnect it. It is something like this. Right? Because we got 6 terminals here and we got 6 terminals here. Okay? And if you want the configuration 3-phase to 2-phase, this should be the configuration. Okay? We interconnect the terminals. That's why, according to the concept, okay, this transformer is not actual. The flux experienced by this transformer is not the same flux as this one. That's why they are. They are not connected magnetically, but they are connected electrically because we interconnect the connections. Well, that's the meaning of this. We interconnect the different terminal connections, so they are connected electrically, but not magnetically, because the flux of this is different from this one. This is another transformer, and this is another transformer. So their fluxes are actually different, but they are connected electrically because we are connecting the terminals. Okay, we are connecting the terminals to obtain a 3-phase to 3-phase, 3-phase to 2-phase, or 2-phase to 3-phase. Okay? So if we try to define, I will try to repeat it, the teaser transformer, it has an 86.6% tap on both the primary and secondary. Okay, this is the teaser transformer. This is the primary winding, and this is the secondary winding. And there is a tapping on the primary, which is 86.6%. And there's a tapping on the secondary, which is 86.6%. There is a purpose for this 86.6%. Later on, I will try to explain it. For the main transformer, this one, it's a separate transformer. It has 50% tap on both the primary and secondary. The primary side of the main transformer is this portion here. This is the iron core. And the secondary side is this one. And according to this description here, it has a 50% here, 50%, 50%, 50%. Okay? There is a reason for this 50% here. Because later on in the so-called summation of the voltages, this 50% here in this 86.6% has a, what they call this purpose in which to arrive at a certain voltage. So maybe Mr. Scott or Engineer Scott, okay, design this one for it to have a 50% here and 86.6% here. Oh, that's intelligence. Okay. What's next? Okay, I will try to bring out the purpose of this 86% tap. Why there is a tap on the primary and secondary for the teaser transformer with the value 86.6%. Why not 75% or 60%? Why it is 86.6%? Okay, I will try to read the, what you call this, the reason behind it. Measuring from the end of the teaser to its end of the main transformer must equal to the voltage feeding the main transformer measured vectorially. This is hard to understand, but if we try to express this one in terms of an equation, it is something like this. This is the teaser transformer. One end of the teaser, we connect it at the center tap of the main transformer. Okay, one center tap. This end here is connected to the center tap. Okay, and this center tap here, this portion here got an 86.6%. This is 50%, and this is also 50%. According to this purpose here, if we try to take this sum, okay, where we are measuring voltage here, from this terminal here, okay, to this terminal, okay, it means we are measuring the voltage BA and voltage BB. So I place it here, voltage BA plus voltage BB, okay, that's according to this note here. And the voltage A plus voltage C. Okay, so voltage A plus voltage C. Okay, and this should be equal to, according to this, must be equal to the voltage feeding the main transformer vectorially. And the voltage feeding the main transformer is actually the voltage between B and C. And this should be equal to voltage B sub B and B sub C. And from my designation here, I will just put this one as capital letter B. Okay, vector. Oh, that's the meaning of this. If there is an 86.6% tap over here and there is 50% here, according to this description here, if we try to measure the voltage across this, okay, this should be equal to the voltage across this, and this should be equal to voltage across this. So actually, we are having a three-phase. Balance three-phase. Okay? If this is 86.6% tap and this is 50% and this 50%, if we try to measure the voltages across this, and across this, they are all balanced. Okay? And that is three-phase. Okay, and that's according to the definition. Okay, one end of the teaser, we connect it at the center tap, and if we try to measure the voltage from this point here to the 86% tap to this terminal, okay, and this should be equal to the voltage from this point here to the other terminal of the center tap, okay, and this should be equal to the voltage being fed to the so-called the voltage fed to the main transformer is actually this one. That's why this first voltage here plus the next voltage, what do you call this one should be equal to this voltage. That's why B sub A plus B sub B, B sub A plus B sub B is equal to B sub A plus B sub C. And this should be equal to B sub B plus B sub C. The voltage B sub B plus B sub C is actually the total applied voltage to the main transformer. And this should be equal to B sub B plus B sub C, and this should be equal to simply capital letter B. It's balanced. This is capital letter B, this is capital letter B, and this capital letter B. If this stuff here is 86.6%, and this stuff here is 50%, and this is 50%. So that's the reason why on the teaser transformer, there is a tapping of 86.6%, and on the main transformer, there is a tapping of 50%. Okay, we will perform this one vectorially. Vectors. We are computing complex numbers. For the other variation, okay, if we try to convert three-phase to two-phase, it will be something like this. The left-hand side is equal to this. For the right-hand side, it is this. So this is a single phase. So in total, this is two-phase. 4 wires. Okay. On this side here, the other terminal of the teaser is not connected to the center tap. So we will connect a first load here, which is single phase. And for the main transformer, we got two terminals, okay? This is line 1, this line 2. We connect another single phase load. So a single phase and a single phase will be two phase. Okay? 4 wires. So this TT transformer is actually very flexible because if we could change the connections of the terminals, we could make a 3-phase to 2-phase. 3-phase to 2-phase. First one is 3-phase to 3-phase. Right? 3 voltages which are equal. B, B, B on the secondary, on this side here, this should be B, B. If this is 86.6% tap, and this is 50%, and this is 50%. So there must be a reason behind why this is 50%, and this is 50%, and this is 86.6%. Because if we try to measure the voltages across these, okay, they are all equal, and it is considered 3-phase. Okay, that's it, guys. That's the main purpose of a TT transformer. That is a conversion from a 3-phase to 3-phase. 3-phase to 2-phase. We just change the interconnection of the terminals. We could determine a 2-phase. And for a 2-phase to 3-phase, I cannot place it here. We lack spacing more. Okay. So from 3-phase to 3-phase, this should be the connection. 3-phase to 2-phase, it's almost the same connection, okay, except that the other end of the teaser is not connected to the center tap. It goes to the other end of the first phase, and the, what I call this, the main transformer, it got 2 lines also coming out, and that is considered single phase. So a single phase and a single phase will be considered 2-phase. It was specified for a while. Okay, that's it, guys. That is what they call this SCAT or TT transformer. The main purpose of this one is actually to change from 3-phase to 3-phase, 3-phase to 2-phase, and 2-phase to 3-phase. And according to the definition, this teaser transformer and main transformer are connected electrically, okay, electrically, but they are not connected magnetically because this is a separate transformer and this is a separate transformer, meaning the flux of this is different from this, and they are not connected because it's a separate transformer. That's why, according to the definition, SCAT or TT transformer is a transformer which are connected electrically but not magnetically. So this is actually two separate transformers with 6 terminals coming out and 6 terminals coming out, and to obtain 3-phase to 3-phase, 3-phase to 2-phase, or 2-phase to 3-phase, okay, you just change the interconnection. Okay, good evening from Los Angeles. This is Professor David J.